Is it recording? Oh, it is. Okay. All right. So only 2 questions this week. Not too difficult, but like very like long and not long. Just there's not a lot of physics. There's pretty much algebra. So for the first one, okay, you're just gonna try to derive the equations of motion for a scalar field, and the difference between this and the one in particle physics is that now you have to do it in an expanding space-time. Okay, so it gives you the action, which the only real important part you need to know is just the Lagrangian for this part. So this is just your L. And then it gives you the Euler-Lagrange equation. And the only difference here is that it uses this delta instead of like a derivative. I'm not 100% sure why it is. I'm pretty sure it's just a notational choice to not confuse it with like, because usually you'll see like dl dq dot or something like that. So I think it's to not confuse it with the actual 4 derivative. So it uses delta, but then you can think of it as the same as like what you see here. So it's just a notational choice. It's a variation. Yeah, technically it is. I haven't thought too hard about it in the math sense. Yeah, it works out the same if you once you rearrange the equations and everything and then plug the terms in, you can treat it just as a derivative, like normally how you use a derivative. But yeah, technically it is from calculus of variation, but I haven't been able to come up with a case where there's some subtlety you need to be careful of. So feel free to just treat this as a derivative. Okay, anyway, and hopefully you've seen this notation before. So if you just write it as G here, that just means the determinant of your metric, G mu nu. All right. So yeah, might as well get the determinant out first. So your G mu nu in this case in FLW is just going to be the diagonal 1 minus a squared minus a squared minus a squared. And so the determinant would just be minus a to the 6. Okay, and so the square root of the minus of the determinant would just be square root of a to the 6, so equals a cubed. So that term is sorted. You can just sub this in whenever you see square root of minus g. And okay, then now we'll move on to the Lagrangian. So I need to sort this Lagrangian out before we can put it into the Euler-Lagrange equation. So here we're gonna turn both derivatives downstairs with the metric. So g mu nu, d mu phi, d nu phi, minus v of phi. And here the g mu nu upstairs is just the inverse. So then you'll get 1 minus 1 on a squared, minus 1 on a squared, minus 1 on a squared. Okay, and because you're summing over, the G mu nu is basically summing over these indices. So you can actually split them up into the time and spatial part explicitly. So it makes it easier to see exactly what's going on. So rather than G mu nu summed with these 2 derivatives, you get G00 summed with D0 phi, D0 phi, and then plus GII. So the spatial parts summed with DI phi, DI phi, minus V of phi. You don't get any IJ or 0I or any off-diagonal terms because your metric is diagonal. So you only end up with the diagonal components. And that was a lot clearer. So D0 is just time derivative. So these 2 are just going to be phi dot. And these DI phis are going to be just the gradient. So these are grad. And then we know G00 and GII from the metric. So we can just explicitly write this out as phi dot squared minus 1 on a squared grad phi, and there's 2 of them, so grad phi squared, and with a V of phi, minus V of phi. And that's your Lagrangian. So we're now at a point that we can actually just put this into the Euler-Lagrange equation now. Okay, so for the Euler-Lagrange equation, I'm going to do this thing again, where rather than having d mu going through all four indices, I'm going to separate out the time and the spatial parts, so it's a bit easier to manipulate. So the EL equation, you get d0 of delta, not minus, square root of minus g L delta, just the 0th component, and then plus the spatial part. And then minus the last one was just a derivative with respect to the field. And this whole thing is equal to 0. Okay, and now it's pretty clear. So the first one is with respect to phi dot. Second one's with respect to grad phi. And in this equation here, you have your phi dot grad phi, and the only thing that's dependent on phi explicitly is the potential. So these three derivatives, or like variational derivatives, can be pretty trivially just read off from this Lagrangian here. So first one, okay, yeah, just write it in to be clear. So first one will give you d dt from the d naught, and then in the bracket you're going to get an a cubed from the square root of minus g, and dl d phi dot will just give you this 2 phi dot with a half, so it would just be phi dot. So all is left is just 1 phi dot. And then for the second one, same thing. So, but this will give you a grad. And then this thing will give you first an a cubed. And then from the derivative, you get a minus 1 on a squared, and then just 1 power of the grad phi. So you get a minus 1 on a squared grad phi. And then the last one, you just get an a cubed plus a derivative of the potential with respect to phi. So this one is nothing to really write about, and equals to 0. And now you just have to go through these derivatives. The only thing is the first one, because both the a and the phi dot are time dependent. So then you end up with like 2 terms here, but the rest of them are pretty straightforward. So you get a cubed phi double dot plus 3a squared phi dot a dot minus this one. It gives you 1 factor of a, and then the grad phi with the grad phi again, so you get a Laplacian of phi, and then the last one is just the same. So did I miss the minus sign here? Yes, I did. So this is technically minus. This is just plus, because there's a dl d phi will give you a minus dv d phi, and then there's already a minus sign here. And I forgot to cancel this out. So this is plus a cubed dv d phi is equal to 0. And to get it to the form that you want it, all you have to do now is just divide everything by a cubed. So you get phi double dot plus 3 a dot on a, which is just the Hubble rate. So I can just write h in there straight away. And then phi dot minus grad squared on a squared phi plus dv d phi, and it's equal to 0. And I think that's what you started out to try to find. Yeah, that's it. So that's the answer. Cool, no problems with that, just algebra. Okay, if no questions, then we'll go to the second one. where did I put it? Oh, down here. Okay, so for this one, you want to show that the first two Hubble slow roll parameters, epsilon h and eta h, are related to the potential slow roll parameters, eta v and ev, epsilon v, and you're going to show these two relationships. Okay, so to start this, you just want to set it up with first looking at the first Friedmann equation. And going to look at it in the, of course, during inflation. So during inflation, the entire universe is dominated by the inflaton field. Dominated by phi. So then your first Friedmann equation, h squared equals a pi g on 3. And the rho would just be given by the energy density of the inflaton field. And in that case, it's just 3 half phi dot squared plus v of phi. So you have the kinetic term and the potential term, and those are the only energy contributions from the inflaton field. And then also want to bring out the Klein-Gordon equation. So the Klein-Gordon equation, in this case, because during inflation, everything is expanding out so quickly, then like whatever inhomogeneity you have is going to be diluted out. So you can assume in this regime, you have a homogeneous Klein-Gordon equation. Any kind of primordial fluctuations will be so small at this point that you don't have to care about it just now. So homogeneous Klein-Gordon equation would just be taking the answer we have here, except we wouldn't have this term because it has a spatial variation. And as we said, in homogeneous universe, spatial variation will equal 0. So you just end up with these three terms. So your Klein-Gordon equation would just be phi double dot plus 3h phi dot plus v dash. The dot will be the time derivative. Dash will be the derivative with respect to the field phi, equal to 0. Okay, so now that we have these two equations set up, we just want to now apply the slow roll approximation. So if you remember, that means your potential for the inflaton field is dominating over the kinetic term. So it's rolling very slowly. And the requirement for this is that your field has actually been stuck on the Hubble friction. So your Hubble friction in the Klein-Gordon equation is much larger than the actual acceleration of the field. So this is like stuck by friction. So you can think of it as like an extremely overdamped oscillator where the damping term is much larger than your driving term. Or not driving term, your actual acceleration. Okay, so with these two approximations added, then you can even simplify the Friedmann equation and Klein-Gordon even further. So your Friedmann equation wouldn't have this kinetic term at all. So if you assume this is a really big difference, then you can treat it with just the potential term. So that means your h squared in this regime is approximately just a pi g on 3 v of phi. And similarly, your Klein-Gordon equation will be dominated by the damping term. So then your Hubble friction is the only thing that's really doing anything here. And that's approximately equal to minus v dash phi. I don't know why I took it to the other side. Doesn't really matter. It's the same thing. Okay, so now it gets a bit like kind of I do this because the algebra eventually works out. There's not much physical motivation for why I do this. So the next step is to take the time derivative of the Klein-Gordon equation. So I differentiate with respect to time on both sides. So I get d dt on the left, my h squared, and that's equal to d dt of a pi g on 3 v of phi. Okay, I don't need to expand the h out because the the slow roll parameters, they all only just depend on h and h dot. So I don't need to know exactly what the a's time dependence are. So I can just do this time derivative with h. So I end up with 2h h dot, and that's perfectly fine. And equals the right-hand side, you only have the potential that really evolves with time. 3 dv dt. Okay, but dv dt is not very useful for us because we really, at the end of the day, want to get all the, if you see all the potential terms in these expressions, they're all with respect to the actual field phi itself. So you don't see any v dot terms around. So that already tells you that you're gonna you're not gonna be having a good time keeping this around. So just do a chain rule to change it into the derivative with respect to phi to make things easier. So you end up with dv d phi and a phi dot. Okay, so now that you're up to this stage, then you want to divide both sides by the essentially the Klein-Gordon not Klein-Gordon equation, by the first Friedmann equation again. So h squared equals a pi g v on 3. Dividing both these sides by that, then not dividing both sides by that. So you're dividing it by itself. So left-hand side divided by h squared, right-hand side divided by this. So you end up with 2h dot on h, and that's equal to v dash on v phi dot. Okay, and now we can sub in the phi dot with the Klein-Gordon equation. So phi dot is equal to minus v dash on 3h given by the kg equation. Yep. So then you get 2h dot on h is equal to minus v dash squared over 3h v. Okay, and then now you sub in this again. So you sub in 3h squared is equal to a pi g v. So then you get 2h dot on h is equal to minus v dash squared on v. And then where do my h's go? So this will be h on top, a pi g v. Okay, and then do some rearrangement. Take the h on the left-hand side, take the 2 to the right-hand side, and you get minus h dot on h is equal to v dash on v all squared 1 over 16 pi g. So this v goes in there and the whole thing becomes squared, and then this 2 comes down here. Okay, and that's it. And the left-hand side now is epsilon h, and the right-hand side is epsilon v. So that's the first relation where epsilon h is approximately equal to epsilon v, given all the assumptions that we made. Yeah, is that all good? I know it's like these steps don't really make a lot of sense, but surprisingly, this is actually something rather common if you're doing research in cosmology. You end up having to derive these things with similar kind of trial and error in real life. So it's not that far removed. It's not like we made up this exercise just for the sake of it. Before you actually get to do any calculations, you do have to go through some of these equations just to try and massage them into another form that's maybe more convenient. So you kind of try different things to sub in until something works. And here we're just showing you the final trial and error that actually worked. Okay, and no questions, and we go for the second relation. Okay, for the second relation, then we're going to start similarly, but except this time we're going to take the time derivative of the Klein-Gordon equation. So that means we take d dt on both sides of 3h phi dot. And on the right-hand side, it'll be d dt of minus v dash. Okay. Left-hand side is easy. You just get 3h phi double dot plus 3h dot phi dot. On the right-hand side, it, again, is you just have to do a change of variables. So you get minus v double dash, but then pick up another phi dot on the right-hand side. I'm getting a phone call, sorry. No, all good. All right, and now you just pretty much rearrange this thing a little bit. So I take this to the other side, so I get minus 3h phi double dot equals v double dash phi dot minus 3h, oh sorry, plus 3h dot phi dot. Okay, and then divide both sides by 3h. Well, I haven't used this notation in a while, since like primary school. Okay, so you get minus phi double dot on h equals v double dash 3h squared phi dot plus h dot on h phi dot. Did I get this correct? No, this is a h squared, sorry. Yep, okay, everything works out. Okay, and then now divide everything by phi dot. So you get minus phi double dot h phi dot equals v double dash 3h squared plus h dot on h squared. Okay, now it's getting closer. Okay, the final step is just sub in the first Friedmann equation again. So sub in 3h squared is equal to a pi g v into this term. So then you end up with minus phi double dot on h phi dot. It's equal to 1 over a pi g v double dash on v plus h dot on h squared. Okay, and now this thing is eta h, this thing is eta v, and this thing is minus epsilon h. And okay, that's just the backwards of the relation that we wanted. We just wanted eta v equals eta h plus epsilon h. Well, like approximately, since we took a couple of approximations. But yeah, that's the second one. Second relation. And that's it. Pretty straightforward this week. Just a little bit of algebra. Okay, any questions?